Hello. So my name's Elias, and I will be explaining my lane detection algorithm today. First off, I want to apologize in advance. I have a little bit of a cough right now, so I'm sorry if that interrupts some of the video. So a majority of this pipeline was started in class, but we're going to go over that part as well just to make sure we cover all our bases and get an overarching view of this algorithm, and then I'll go into the parts that I implemented on my own to be able to detect this in videos, in the two test videos specifically. Um, okay, so first, we have our imports here. Not all of them are necessary. I have them there as just like a baseline. And we go in and check that our packages were imported properly. Then there's some comments to start off. Um, this is just my template for our homework assignments. So the first thing that we're going to define is some variables. These are blank variables for our previous left and right lane lines. These we're going to use later in our algorithm. So our first step in the pipeline is to snip the image so that we get a better view of just what we want to focus on. In the next step, we are going to throw a mask over the image so that we can get a, a view of just the lane that we would like to focus on for this lane detection algorithm. We then threshold this image and convert the image to HSV colorway um, and define an upper and lower bound for detecting these lane lines um, and produce that over the mask. Next, we blur the image to get a better gradient and be able to define edges and lines better later down our pipeline in the next step, which is our edge detection using CV2's canny function. This will detect the edges in the image. And then we will draw our huff lines on this image using a huff transform. And this will identify any of these edge lines in the image that will be our lane lines. That'll be the basis for our lane lines. In our next function, we are going to estimate these lane lines. So this is where we start off on our new content for this lane detection algorithm. And here I define some blank arrays. And to go into, we start off with an if statement going into if our lines is not none, which basically says, do we detect any lines or do we not detect any lines? If we do, then we go ahead and keep going in our function here. So for our lines that we detect, we are going to now filter these lines based on their angle. This is how we differentiate between the left lane line and the right lane line. For this algorithm, for these specific videos, the way I have done it is if theta is less than pi over 2, then we are going to detect that as the left lane line. And if it's greater than pi over 2, we're going to detect that as the right lane line. This is also where we, compute the mean of our lines to get a better average of what these lines will look like, because in our Huff transform, we detect a lot of lines and get multiple lines. So we want to narrow that down to define one good line that we can work off of for the rest of our algorithm. In our next function, we actually plot these lane lines. So this is where our previous lane line variables that we defined much earlier in this algorithm come into play now. We also are going to define our bottom of the region of interest. This will also come into play later in the algorithm. So this is where we end up smoothing, as you'll see later when we actually show this video. The lines were flashing on and off the screen. So in order to reduce that, I have created a little if statement here for both the left and the right lane lines, where I will set the lane line as the previous lane line if the lane line is not detected in that frame. So this will make sure that if there are no lane line detected in that moment, it will set as the previous lane line so that we can remain continuous and consistent throughout the video. And then we go on to actually plot these lane lines. It is the same algorithm for both the left and the right, adjusted a little bit because they are in different regions of the image. So first we enter an if statement to make sure that we actually have a left lane line to calculate, and then we actually go into it and start defining our line. We first do the cosine and sine of the data to get a idea of what angle this line is at. We will then define a point on the line using that, and using our row values from our transform as well. We will then pull that and get two more values off of off that original value we calculated off the cosine and sine of the row and thetas calculations. And here we have some typecasting to make sure that we get integer values for this. We also use our original points, and we either add or subtract a multiplier value, which in this case is 30 and 175 for our x1, y1, x2, and y2s. And we then multiply by our values calculated earlier using the row and theta. For our y values, we will now use that bottom line that we defined, because in the video they were initially being set much higher than the actual lane line, still at the correct angles, but much higher than where we wanted them to be detected. So we had to add an adjustment for that to make sure that they actually detected on the lane lines. Also, this multiplier here was adjusted to make sure that the lengths were correct. The lengths were correct for this video, so that they weren't crossing over the entire image, just so we made sure that they were within the scope of the lane lines. We then draw our lane lines here. The left one will be in green and the right one will be in red. And then we use the same exact calculations for the right lane line down here. Our next function that we define is the process frame, and what that's going to do is essentially just go through all of those functions we just described and return that frame with the lines drawn on it. If we then go into our main function that will actually run the code, this will open the video file, get the frame dimensions just for the image processing. This is just to save the video. It's not necessary, but we did it just so we could have the video saved for us. And then we enter a loop here that makes sure that we can get the next frame. Then we go through our process frame function, which will go through all of our other functions. And then we will go into showing these frames to the screen, writing them, if a break, just in case we need to end it early, and then we will exit out of this video. So now I'll go ahead and show you what this looks like. And as you can see, there's a little bit of a mess up in the beginning because they're changing lanes, and also because there are no previous lane lines defined to base our lines off of. But now you can see these lines are fairly smooth. There's some shakiness just with the dots and the lightings. As you can see, the right lane line is a lot smoother than the left lane line, again, because the left lane line is dashed and the right is solid. But as you can see, it gives a fairly good picture of where the lane lines are and remains fairly consistent throughout the video. So we will just play through that. As you can see, the difference in road color also had a slight effect on it, just because our values are not extremely tuned for that type of scenario right there, but it still stayed relatively correct. In our code for the next video, we have a very similar code, almost the exact same. A difference that we made here is a difference in our upper and lower bounds to define the lane lines. This is because there was a difference in lighting in the video, and I had to do some debugging to optimize these values. But what I noticed is when we changed the video to the HSV colorway, the lane lines were not a lot more of a bright red as opposed to maroon in the last video. So as you can see here, I adjusted for that to be able to make sure we are just capturing those lane lines. Everything else remained fairly similar to it. I have some debugging ones in this just so I could figure out the optimization for it, because again, the lighting was different in the other video. So now I will show you this one and how it is a little bit different. So here you can see the lighting is much, much brighter. And our lines, although they're continuously on the screen, they're a lot shakier. This could be because of the speed of the video. It could be because of the lighting and the difference in the color of the road and the lines and the fadeness of it. As you can see, it's a little bit more shaky, but it works fairly well, and still remains pretty consistently on the lane lines throughout the entirety of the video. It gets a little bit more stable at some points and a little bit more unstable at other points. This could be because of shadows from other things, like cars passing by or signs that affect it. But it's still a pretty good representation of what's going on. um, Again, some issues that I ran into were the change in lighting, changing the colors of the lane lines, which is something that we needed to account for. The adjustment from the top, from the shifted up, from the snipped image to the original image, which we needed to shift back down, and adjusting the length of the lane lines so they were just within the scope of the lane lines. Those were some of the issues I've run into while trying to debug and optimize the code. For maybe some improvements down the long run, I would think that there might be a way to improve the dynamic thresholding of the video to be able to adjust for many different lighting conditions, as well as create a better idea of, instead of just defining it as the previous lane lines remain continuous, maybe having a further reaching camera that we can be able to detect the lane lines for a longer time so there's not as much flashing, and we don't have to define them as previous because that may not necessarily work in all situations. In terms of the hardware, maybe a slightly better camera so we can detect contrast a little bit better, maybe see a little bit farther in more detail so we can detect a little bit further what's ahead. But yeah, I think that this lane detection algorithm works fairly well for the example videos. It does need to be optimized and tuned for situations, but in the future, I think there are definitely ways to improve that, optimize that, and have it work blanketly across multiple different scenarios. Yeah, that is all. Thanks.